Hey everybody, welcome back for my third and final video on drawing free body diagrams. I hope everybody's been really nice to my substitute teacher. I should be back on Thursday after the Wednesday break. I was looking through the learning set today and I realized that question 73 was really tough. It's multi-step, it's complicated, I expect a lot of students to have trouble with it. So I thought it was a good opportunity for me to help you knock off one of the more difficult problems on your learning set. So let's take a few minutes and go through it together. The question reads that a 65 kilogram diver jumps off of a 10-meter tower and dives into the water. It then asks two questions. It first asks, one, what's her velocity when she hits the water? And two, the question reads in the book, if she slows to a stop 2 meters after hitting the water, what is the net force on her body? Now I'm going to go ahead and cross out the 2 meters and pick 2 seconds. It turns out that the 2 meters requires that we use a third kinematics equation that we never actually covered last unit, but 2 seconds should be totally solvable based on the equations that we have from last unit. So let's go ahead and take a look at my reality sketch. I went and drew a lighthouse, and there she is, instantly regretting her decision to jump off of a 2-meter tall tower. It's about 30 feet. So there's my reality sketch. Now for our physics diagram, we need to draw two main things. We need a motion diagram showing her acceleration to the water and negative acceleration after hitting the water. And we also need a force diagram, a free body diagram, showing the force on her body after she hits the water. So I'm going to go ahead and try to draw a relatively straight line here. And this will be our motion diagram. Okay, and I'm going to go ahead and put in a little mark just to divide. This is roughly where she hits the water. Okay, so now when she jumps, you have a dot to show her position, and her position changes very slowly at first. She has low velocity, and then as she accelerates, your dots, just like in last unit, are going to get further and further apart. So this should show her acceleration towards the water. All right, now when she hits the water, she very rapidly slows down, so she shows negative acceleration. So maybe there's a dot of her at the water, and then pretty far apart, but they're rapidly going to get closer and closer together. Okay, there we go. It's not pretty, but it'll work. All right, now we need to add a couple things to this motion diagram, right? We need to specify that, let's see here, her acceleration is above water is equal to a positive 9.8 meters per second, and below the water, below the surface of the water, her acceleration is equal to, we don't know. It's going to be negative because we set down as the positive direction. So it's going to be negative, but we don't know. So I'll just put a question mark there as a placeholder. We also need to put in, the classic information. We need to know her initial position. We need to know her initial time, initial velocity. Okay? We also need to know her final time, final position, and final velocity. So I'll put it down here. That's going to be x sub f. Let me back up. There you go. X sub f, t sub f, and v sub f. Oh, that's ugly. Let me try that one more time. X sub f, t sub f, and v sub f. Now, we also need a third set of points here. We need to know her position at the surface of the water, her time at the surface of the water, and her velocity at the surface of the water. Okay, so let's fill in what we know. When she first started, this is the easy part. Her initial position, let's just set that equal to 0. Her initial time, 0, and her initial velocity is 0. That's going to be 0 meters, 0 seconds, and 0 meters per second. Let's see. At the water, we know that she was 10 meters in the positive direction. Her time, we don't know. And her velocity, we don't know. In fact, it asks for those. Okay. And under the water, we know that her final position is going to be 12 meters because we said she went 2 meters through the water. Her final time, we don't know. And her final velocity, we know is going to be 0. All right, motion diagram complete. Then very quickly, we need to do a force diagram. So go ahead and draw a dot. That's going to be the object that the forces are acting upon. That's our diver after she hits the water. Now in the water, you could argue that she has the force of gravity pulling her down, but she also has the force of water pulling her up. So she's buoyant in the water, so let's go force of gravity on the diver. And then I'm going to do a much bigger arrow, or a significantly bigger arrow, and that's going to be the force of water on the diver. Now what's happening here is she's going through the water with high velocity, but the upward force of the water on the diver is greater than the downward force of gravity, so it's slowing her down. She's showing negative acceleration. Now the first question asks, what is her velocity when she hits the water? Unfortunately, we can't calculate that directly. We need to do that in two steps. We first need to find the time that it takes for her to hit the water, and then we can use that to find the velocity. So here's my motion diagram, and I'm going to go ahead and push that off to the side, and let's go ahead and get started. So I'm going to have a physics rule, PR, and that's going to be a really long equation from last time. So her position when she hits the water is equal to her initial position plus her initial velocity times the time interval, but that's going to be the time that she hits the water minus the initial time, plus 1/2 times her acceleration due to gravity times her time interval squared. Oh, I'm out of room. Let's see if I can fit it in there. Okay, there it is, squared. It's not pretty, but it'll work. So our calculations go something like this. The water is at position 10 meters. Okay, her initial position is 0. Her initial velocity is 0, so that zeroes out, plus 1/2 times 9.8 meters per second squared times, now remember her initial time is 0, so this is going to be TW minus 0 squared. This should be kind of quick to solve. I'm going to go ahead and do the algebra. If you have any questions about this, just ask me on Thursday when I'm back in class. But let's see, so the calculations go like this. 10 now is just going to be equal to 1/2 times 9.8 meters per second times the time that it takes her to hit the water squared, which means that this would be, I don't know, this is going to be, what, 4.9, so I get that 10 over 4.9 is equal to T sub W squared. We're going to take the square root of both of those, and we're going to get that T sub W is equal to about 1.43 seconds. Okay, there it is. So we have the amount of time that it takes her to hit the water. Let's go ahead and take that number and let's use that to find the velocity that she hits the water with. So we're going to have a physics rule, and this is going to be the velocity that she hits the water with is equal to her initial velocity plus her acceleration due to gravity times the time interval. That's the time she hits the water minus her initial time. And I would just substitute in real quick. So the calculations are going to say that the velocity that she hits the water with is equal to 0 plus 9.8 times, now we know it's 1.43 seconds minus 0. Okay, so the velocity with which she hits the water is about 14.0 meters per second. There we go. And I think we've answered the first question. So now that we know her velocity, the velocity that she hit the water with, we can go ahead and start on the second part of the problem, which asks what the net force on her body was. Now sigma F equals ma. So in order to find the net force on her body, we need to first find the her acceleration through the water. So let's go ahead and start with the acceleration equation from last unit. So physics rule is going to be her acceleration through the water is equal to her change in velocity. So that's her final velocity in the water minus the initial velocity she hit the water with, that's v sub w, over the time interval, t sub f minus t sub w. Okay, now we know that her final velocity is going to be 0. She's slowing down to rest. And the velocity she entered the water with is 14 meters per second. Now the time interval here is interesting. We just know that it's a 2-second time interval, as in she's slowing down over the course of 2 seconds. So I'm going to go ahead and just write it down as 2 minus 0. So that means that her acceleration through the water is equal to negative 14 over 2, which is equal to negative 7, and that's acceleration, so it's meters per second per second. So she's slowing down really fast. Okay, so with that acceleration, we're really close to wrapping up the problem. One last step. So now, let's take our final equation. That's going to be physics rule. That's going to be sigma F equals ma. The sum of the forces on the diver is equal to the mass of the diver times the diver's acceleration through the water. So remember the intermediate step. You got to write the actual forces. So the net forces on the diver, or the sum of the forces, are really just going to be the force of, let's say, the water on the diver. Okay, you could add the force of gravity on the diver as well, and that could be a big classroom discussion as to whether that's relevant or not to the problem. And that's going to be equal to the mass of the diver times the diver's acceleration through the water. We've already designated that as A sub W, so let's go ahead and keep it consistent. Now, the force, the net forces, the force of the water on the diver, are then equal to, in the calculations, drop in the numbers. The diver, I believe, weighs 65 kilograms. And we just figured out that she had an acceleration of negative 7 meters per second per second. Multiply those together, and I think that comes out to, let's see, the force of the water on the diver, or the net forces, are going to be equal to, what is that, 455 kilogram meters per second, or 455 newtons. And there it is. Problem solved. Again, feel free to rewatch the video on your own at home, pause it, rewind it, whatever you need to do, and go ahead and come to me with any questions on Thursday. I hope this helps.